To our first main part in the course B01 on why we want to manage our data. So the reasons for this are very, very good. It's worthwhile investing in this, in particular to things like improve your decision making and understanding of the data sets you have, allows you to do better research that where the data sets attract more effectively. You can reuse them for future projects, which is very important. You also find that you're able to do things more efficiently in the long term, and also contributes to the community and enhances the prospects of people that you're working with. There's also a compliance and governance issue, particularly if we're spending large amounts of funding money on generating these data sets, then we all have a responsibility to ensure that the data is cared for carefully. And notably, what I want to emphasize in this course is that if you're a data scientist, then you're a data scientist. Data underpins all aspects of our work. It's worth bearing in mind the data sets will become larger and more complex. So by taking part in this course, you'll be one step ahead. Linked to this, we have to reflect on the reality that there's major issues with reproducibility in biological and biomedical science. If you survey researchers, the majority will agree that there's a significant crisis or that it's certainly a major issue. If you look at other areas beyond biology, you'll see that there are similar issues, that experimental reproducibility is poor, especially when you consider the amount of funding that's used in this area. That's a bit disconcerting. Why does this happen? Well, a major issues are that there's pressure, especially on young researchers, to generate results, even if they're maybe have dubious origins, and really that pressure comes from the top. And it kind of manifests in the generation of results that actually don't stand up. We typically see, especially in biology, the use of small sample sizes that have insufficient power to actually measure the effect of interest, and that leads to a wider variation in the effect sizes that are estimated, which means that you can get very conflicting results as a consequence. Related to this, we also see p-hacking, and then also harking, hypothesizing after results are known, and just errors, sloppiness, lack of quality checking. All these things are very, very common in biological sciences. And if you look at any particular research paper, you'll find that these things can be often found. So we know, for example, there's selective reporting, pressure to publish, poor or inadequate statistical analysis, lack of replication, insufficient oversight monitoring, which really means insufficient checking for errors that do arise. Often the data and code are used as unavailable, the experimental design might be poor, and it's just hard to get the original data. So this is a very major challenge. And what we know is that large data sets are getting larger and more diffuse. We find that there's new technologies and new data types, but maybe not a good understanding really of these new technologies and data types. Organizing, storing, and managing large data sets is expensive, complicated, and is an area in and of itself. So this leads us to the tragedy of the commons, and often means especially for young researchers, they're given a bunch of poorly managed, disorganized data sets that you didn't create, but you're the person that has to manage, and you're in a short-term contract, and you're given old results you don't know how they're generated, and you don't know, you're just landed into a project and you don't know what you're going to be doing, what data sets you're going to use. So you're often quite confused, and really you're starting from a situation of data at the start of a project, where in 2 years' time you are moving something onto some other role in a different institution or a different country. So this kind of just leads to poor data management overall. So this next case is cartoon of this, where first made a fully automated pipeline that collects and processes all the information we need. This person asks, is that a giant house of cards built from random scripts that will completely collapse the moment anything input at the moment any input does anything weird? And of course, that we can see that a lot of the tools that were developed of whatever nature are maybe not as robust as we want to be. And linked to this, then we have a lack of ability to actually find the data that has been published. And if you look at, I do work in pox virus genomics at the moment. It is alarming that the amount of lack of raw data that's not released, sequencing data, for example, is really incredible. And uh, my experience during my career has told me that if you can't access the raw data underlying paper, I don't believe it. In short, it's not worth your while even bothering with the paper. Um, a lot of virus genomics papers are not very good, and really that's an unfortunate situation. But they're that's where we're at. Um, I would also advise that if you're reviewing papers that don't release the data in an accessible manner, then that they shouldn't be accepted. And then also you shouldn't cite papers that don't release their data. If you see that, for example, this data will be available upon reasonable request, this is, anti-scientific and not acceptable in the modern era. And there's great examples of this if you look at some meta-analysis of SARS-CoV-2 related research. I think there's one kind of meta-analysis of that released by Strain, but in Spain, um, the 88% of these papers had no research data. A small minority would not share the data. Um, some of the data was shared in the paper. Some would share it via request, and some would share it in the databases. So you can see that there is kind of an issue with data sharing and lack of a systematic way of doing that. And you see then when people run into a new area, they don't really think about the long-term strategy. They're just trying to get papers out. We also know that data sharing means that there's better quality checking because you're sharing with other people and they may not understand it or they may find things about it. A great example of this is the Public Health England's monitoring of SARS-CoV-2 data in September 2022, when they were strangely using Microsoft Excel to analyze this data, which is a bit worrying, to put it mildly. So obviously Excel is very limited for large data sets. It has a limited number of rows. So they lost nearly 16,000 cases. And a consequence of this is that it may have led to additional COVID infections in the 6-week period afterwards. So you see that there was a clear positive effect. And this led to more deaths. So, that's about 0.24 additional deaths per case uh, due to this lack of a awareness about how to check quality of the data. If they had data quality checking mechanisms in place, I'm sure this error would have been found or at least minimized wherever possible. More examples are that 31% of papers have errors in Excel files if they contain gene lists at the end. So this reliance on Excel is really a problem in biology. Another example is this hydroxychloroquine and its links to SARS-CoV-2 treatments. Of course, mechanistically, it doesn't really make any sense that this antiparasite drug would affect viruses. And therefore, when you see these studies releasing by DDR ruled, which is entirely fraudulent, and this guy has produced colossal amounts of fraudulent papers, the lack of underlying data means that you can't really check if the effects is truly real, and there's all sorts of fundamental issues that kind of are easily found once you find out more about the data. So we know that, for example, that inadequate randomization of people to different groups mean that your comparison is not for like for like, and then also you don't. You also see comments by other people. Maybe should know better that large numbers mean that you don't need proper experimental design, which is false. You need proper experimental design, irrespective of what level of numbers you're dealing with. So you get to this thing that you may actually do quality checking, you realize that your data is bad. And that's unfortunate, but it kind of will save you time in the long term that you can say, well, we don't actually know, and maybe we have a better idea of the next steps. you get this situation where you get a bit of strange analysis, p-hacking, hardening, etc. And you see that in many papers. And then you could have other options as well. So when we think about our research culture linked to this, that often in industry or clinical settings, there's tight regulation, careful process control, detailed documentation, ISO accreditation, good manufacturing practice and protocols and whatever. But often in academia, we have this idea that there are no rules, that as long as it worked once, that it's robust, that we kind of look at results and publishing now and documentation later, and that this idea that this is a one-off, we don't need to replicate it, and the kind of approach behind quick and dirty analysis to publish as being the step forward. And there's a lot of pressure from senior scientists on junior scientists to force things out. So data quality matters. We're stuck in a rush from this, that we have researchers who maybe don't have experience in data managing, generating lots of data that's in siloed and not shared properly, and therefore makes it more easy to actually test if findings are correct, and to do meta-analysis and really integrate different data sets. So this can lead to a lot of frustration for people who are trying to, use data sets that have been published but actually are not actually robust. And this means that your results won't be understood, that the data can't be used. It will mean that the work is cited less. It's, fundamentally a waste of resources, waste of funding, and really the lack of, a loss of knowledge that we could otherwise find. And if you find yourself like this, that you Friday evening, you think, oh wait, I've done really great work and I'll finish this on Monday, and then you don't come in on Monday and you don't understand what on earth was going on. That means that you kind of need to document things more effectively. So data management can have good effects for yourself on a day-to-day working basis. So where do you want to be? We'd like to have standard operating procedures, protocols, whatever, for data creation and data management in every lab, just like you have other protocols. Electronic lab notebooks that most people have, of course, will make things easier. And we want to make our data sets machine readable and to have accessible metadata in the form of data dictionaries. We want to apply best practices, and this, is important in the long term for supporting other scientists, which then can be discussed in your CV or researches for the door style narrative CV. We can share data internally or externally. We want to create communities of practice that if you want to get across what you're doing in your data sets, then it's easier to do that with other researchers if you have that easily available. We can link in with other workflows such as lab information management systems or whatever workflows that are there. I want to think about who manages your data. We want infrastructure that supports the tools that we're using. And then also we really have to think about cloud-based environments allow data sharing more easily, and that's kind of where we want to be. So there's no magic solution for your particular area. People work in diverse areas, and often people think, they need AI or something to figure out the data, and what they actually need is just better data management, better Excel, or more fundamental things. One thing that you can use is in the Elixir Europe website. You can click on this website and go to your role. You might be a postdoc, a group leader, or a software developer, whatever it is. You can click on this and you'll find out more about your role and its links to data management. Most of you are probably researchers, and therefore your expectations for data management are that you should be able to write a data management plan, estimate the costs of this for a grant application, ensure your data complies with the regulatory requirements, store your data effectively, use metadata standards that are relevant for your area, document your data as well, get training about data management, including the use of data management tools and data archives. And then if we step up to a group leader level, what's notable is that group leaders should have a data management strategy that's communicated with the lab members. That should mean that, therefore, that people know about their responsibilities in terms of data management, and that people assist each other. Then a fresh pair of eyes often is effective for data management and just making sure that things are more easily documented and well understood. There's a lot of bureaucracy at our institution in relation to the kind of the legal circumstances we work in, and that's also relevant. There should be standards in terms of lab notebooks and the formatting within that for long-term preservation and communication. And there should be, standard things, data organization, data documentation, workflows, protocols, and then systematic approaches to data sharing, data labels, meta-analysis, and importantly, that's also important for grant funding as well, and is a standard expectation. So that finishes this part. Please see the next component on FAIR guidelines.